Hello, everybody. Welcome back to day 2 equilibrium. So yesterday was pretty light and fluffy, very short lesson and just some sort of key but simple concepts to learn on the ideas of dynamic equilibrium. And we looked at those 3 different types. So phase equilibrium, solubility equilibrium, and then chemical equilibrium. So the rest of the chapter is going to be on chemical reactions or chemical reaction equilibrium. And just wanted to remind you that yesterday, the last thing I left you with was to run this simulation and let it reach equilibrium. So I'm just going to pop it up here. So you're supposed to let this thing run until the concentrations were no longer changing. So this particular setup, the reactants are higher on the energy hill than the products, so they would tend to fall down the hill onto the right side. So this one would favor products at equilibrium. I didn't run it long enough to see the final ratio, but I suspect it would be something like 5 to 15 or 3/4 product, 1/4 reactant, something like that. It depended how long you ran it, and it is dynamic, so it is jumping back and forth and changing. But you definitely would have had a ratio that had more products, less reactants. And then in part 3, when you raised this one so that it became endothermic, it would have favored reactants. So when this had reached equilibrium, you should have had more chemical molecules on the reactant side and less on the product side. And again, I don't know that ratio. You had like 40 or 50 molecules in there. So you definitely would have more reactant, less product for this one. And heating it up would just speed the reaction and get you there quicker. Okay, so let's launch into today's topic. So chemical reaction equilibrium. So what I've got here is an experiment that's running, and this is initial. So this is our flask at the start, and it is all iodine and hydrogen separate. So we have H2 gas reacting with I2 gas, hydrogen and iodine. So as the reaction moves forwards, we get some hydrogen iodide forming, and hydrogen iodide is colorless, the same as hydrogen. Iodine is, we'll call it purple for this demonstration. So colorless reacts with purple to make colorless. So you can see as time moves forward, as the reaction progresses, the flask becomes lighter in color as it forms colorless hydrogen iodine and uses up the purple iodine. Now, how would you know when equilibrium has been reached looking at this flask? Empirically, you would say that the color does not change, or the color is constant. When the color is no longer changing, then we have this scenario. The forward rate equals the reverse rate. Every time 2 of these molecules collide and move forward, 2 of these molecules move in reverse to make hydrogen and iodine. So it's at equilibrium. So this is the theoretical description, and this is the empirical description. The observable properties are constant. Okay, so you should be able to look at a reaction graph and explain what's going on in terms of equilibrium. So here's that same reaction of hydrogen plus iodine making 2HI. So let's take a look at this graph. Okay, how would you know when equilibrium is reached when looking at it? So on these graphs, how would you know when concentrations are no longer changing? It would be the point where the lines are flat and they stay flat. Boy, did I ever draw that crooked. Here's my redo. Okay, so whatever time that is, let's say this is 0, 10, 20, 30. So we would say at about 18 seconds, equilibrium has been reached. Is hydrogen iodide the reactant or the product? So if you trace hydrogen iodide back, it started off as 0. So in this case, there was no product, hydrogen iodide. There was zero product, PROD. But as time progressed, the hydrogen iodide started to build up. And then at equilibrium, we would say there was 7 moles of hydrogen iodide. Okay, does this reaction favor reactants or products at equilibrium? Okay, so we started off, what did we start off with? Here's hydrogen. We started off with 6 moles of hydrogen and 4 moles of iodine and no product. That was our initial. At equilibrium, I'm going to make a mess out of this. I should put it down here. H2 plus I2 makes 2HI. And back and forth. Okay, started off with 6 moles, 4 moles, and none. At equilibrium, we have 7, 2.5 of the hydrogen, and 0.5 of the iodine. So here's where we started, here's where we finished. So at equilibrium, we would say it favors products. There's way more products, 7 moles of hydrogen iodide and a lot less reactant. So does this favor reactants or products? We would say it favors products. What amount of reactants and products initially existed? And we already did that, 6, 4, and 0. So there's a lot of information you can get from one of these equilibrium graphs by looking at it and being able to sort of interpret and explain what's going on. It's part of your assignment later today. Okay, now we're going to look at the same system, but instead of a graph, we are going to look at the initial and final concentrations, or initial and equilibrium concentrations, when this thing runs over time until equilibrium has reached. And we're going to do 3 different experiments or 3 different systems. So the first time we do this, we're going to start with 5 millimoles per liter of hydrogen, 5 millimoles per liter of iodine, and no product. And we're going to let it run until equilibrium is reached. When equilibrium is reached, there's our reactants, and here's our product. Now, my question for you is, what is the percent yield or the percent reaction of this thing once it's reached equilibrium? So if we started off with 5 and 5, it's a 1 to 2 ratio. 1 mole of reactant makes 2 moles of product. So if this went 100%, we'd get 10 moles of product. Hopefully that makes sense for you. So our maximum yield is 10. At equilibrium, we got 7.8 out of a possible 10, or 78% yield. Okay, that's system number 1. Starting with reactants, no product, and moving forward. Okay, system number 2, here's where this gets a little difficult, and this is like nothing you've seen in Chem 20. So for this system, we're starting with 0.5, 0.5, and we actually start with some product, 1.7. Now, these 0.5s can both move forward, and if we started with 0.5 and 0.5, we'd get 1.0. So if those go forward 100%, we'll make another 1. So that means our maximum total is 1.7 plus 1 more, which gives us 2.7. So when this thing ran and reached equilibrium, we used up some of the reactant, but not all of it, and we made a little more product. So we went from 1.7 to 2.1 out of a possible 2.7. You plug that into your calculator to get the percent yield, 2.1 out of 2.7, and wow, 78%. Okay, here's where things get really crazy. So now I'm going to mix up my colors. Let's go red. Let's go purple. Okay, so for this experiment, we're starting with no reactant. We're going to start with all product. So maximum amount of product we could get is what we're starting with, 3.2. There's maximum amount. If we got 100% yield, we get 3.2 out of 3.2. We let this thing reach equilibrium, and here's what we get. 0.35, 0.35. So what that means is this went in reverse. It actually ran backwards and made some reactant. And here's what we're left with for our product. So 0.35 of each reactant, 2.5 product, out of a possible 3.2. I don't think you need your calculator to figure this out. 2.5 divided by 3.2 is 78%. Wow. Okay, so here is your big takeaway from this data analysis. The percent yield does not change when a system moves towards equilibrium. You can start with all reactant or all product, and you'll get 78% product every time. Or you can start with a mixture, some reactant and some product, and you'll still get 78%. So what this is telling us is that every chemical system, every chemical reaction has a predetermined equilibrium position that it will reach, and it doesn't matter what you have for ratios of reactants and products. They all end up at the same final spot. And finally, every reaction has its own unique equilibrium position. So hydrogen iodide at this temperature is always 78% product. Okay, that is a characteristic of that equilibrium system. And you're going to discover every reaction has its own percentage at a defined temperature. Okay, that's a big idea to take away. Now, in our last chapter, we talked about oxidizing agents and reducing agents, and we had our table of relative strengths. And we had spontaneous reactions where the oxidizing agent was above the reducing agent, and we had non-spontaneous where it was below. Now, in this chapter with chemical reactions, we have 4 different criteria to describe the amount of reaction. Instead of just spontaneous and non-spontaneous, we use 4 terms. So non-spontaneous, we call it 0%. Totally spontaneous, we use the term quantitative with a single-headed arrow, which means greater than 99%. But then we have 2 in the middle. One where we have reactants favored, so it's greater than 50%, and products favored. Let me back up. Reactants favored less than 50%, and products favored greater than 50%. Okay, reactants favored less than 50, products favored greater than 50%. So we use those terms. Here they are in short term. Non-spontaneous means no product. Reactants favored less than 50. Products favored greater than 50. Quantitative, greater than 99.9%. So 4 different ways we can describe the chemical reactions in equilibrium. And we'll use those terms frequently. All right. So now I'm going to introduce you guys to ICE tables. So in Chemistry 20, every reaction that we looked at was this type. They were quantitative. So this is Chem 20. We assume that anytime you mixed reactant A with reactant B, it went 100% to the product side. Now in Chem 30, we go, that's not good enough anymore, because you just saw in the hydrogen iodide reaction that some of them could be 78%. Some of them could be 16%. Some reactions do nothing. They're non-spontaneous. They don't move forward at all. So we need these more complicated criteria for describing reactions, because reactions are complicated. They aren't all simply all product or no product. They can sit in the middle, where you have both reactants and products in equilibrium greater or less than 50. So how do we figure out where these things sit and how far they move to reach equilibrium? That's really what this part of the chapter is all about. So to help us organize the data and figure it out, we're going to learn how to use ICE tables. And ICE tables are a way of setting up the concentrations and showing the change in concentrations for any chemical system or chemical reaction. ICE stands for I, initial concentration, C, change in concentration, and E, equilibrium concentrations, summarized right there. Okay, ICE. So we're going to build ICE tables to organize the data and make sense of this. Once you get good at ICE tables, they're actually quite a useful tool, and the questions are quite easy. So we're going to look at 3 examples together, and then we'll call it a day, and you can practice this. Okay, so we're going back to our hydrogen iodide reaction. one hydrogen reacts with one iodine to make 2 hydrogen iodide. When I build ice tables, I build them right underneath the chemical reaction. So 1 hydrogen, 1 iodine, 2 hydrogen iodide. Okay, we write down our ice, ICE, and the question tells us that the reaction began with 1 millimole per liter of hydrogen and iodine. So I'm filling that in. That's what it gave me. That was the start. Initially, there was 1, and no product. Now, use your brains. Which way is this reaction going to move to reach equilibrium if we have 0 product? Can it move in reverse and turn 0 into something? Only if it's magical, and it's not. So that's a no-go. Okay. It has to move forward. So this is key to the next line in the table, the change. The change is how does this thing react? What direction does it move when it changes or tries to reach equilibrium? So we know that it is going to move forward. So we are going to lose. And we're going to lose some of this. How much? We go by the coefficients in front. We are going to lose one amount, or 1x. So it says here, this is like algebra. Let change equal x. And because it's a loss, I'm going to put a negative sign. Lose 1x. This one is also going forward. So we're going to lose one amount of iodine. Now it's going forward to the product side. So we're going to gain on the product side. How much? 2 amounts. Right there. So lose 1, gain 2 as this thing moves forward, uses up reactants, and makes products. Okay, the last part of an ice table is to take what you started with, your initial, add the change to get the new equilibrium concentration. So it's like an addition table. So we're going to take our initial, add the change, and that's our equilibrium concentration, 1.00 minus 1x. We started with 1 and we lost 1x. Okay. Here we started with 1 and we lost 1x. Here we started with 0 and we gained 2x. So these represent our 3 equilibrium concentrations, and they all have x in them. So there's got to be a way for us to solve for x and get the actual values. And that's where this comes into play, because we have the answer. Here's the answer to that column. 1.00 minus 1x equals 0.22. Let's cut that off. So now it's just algebra. 1 minus 1x equals 0.22. Rearrange and solve for x, and we have 0.78. Yay! Okay, so now we have x. So now we can substitute it in to these two expressions. So this becomes 1 minus 0.78. Okay, there's our equilibrium concentration of hydrogen. And our concentration of hydrogen iodide is 2x, or 2 times 0.78, which is 1.56 molar. Okay, let's switch up our colors here. So we have just figured out our equilibrium concentration of hydrogen. We already knew iodine, and now we also have hydrogen iodide. So using that ice table, we were able to figure out the equilibrium concentrations of all 3 chemicals. Okay, so it's a little messy, but hopefully that helps you figure out how ice tables work. So we're going to do 2 more questions so you get good at these before you go and practice them on your own. All right, in a certain experiment, 1.000 moles of ammonia was placed in an empty 1 liter flask, 500 degrees Celsius, and allowed to decompose. Ammonia decomposes. So it's going to decompose into its elements, N2 and H2, gas. Ammonia is a gas. Okay, we need to balance this. 2 nitrogen, 2 nitrogen. 6 hydrogen, 6 hydrogen. Okay, so we always need a balanced chemical equation. This thing's going to be in equilibrium, so we'll put our double-headed arrow. And let's organize with an ice table. So off to the side, I'm going to put concentrations. Usually it's moles per liter. Ice. Okay, so what were the initial concentrations? We had 1 mole in a 1 liter flask of ammonia, and it was an empty flask. That's it, nothing else. So those are 0. Okay, this thing has to move forward to reach equilibrium. That's all it can do. You can't take zeros and turn them into something. So it has to go forward. So that means we're going to be losing reactant. How much are we going to lose? 2 amounts. Lose 2x. Okay, because it's going forward to reach equilibrium, we're going to make product. How much? 1 amount of nitrogen, and we're going to make 3 amounts of hydrogen. So we're going to gain 3x, gain 1x, lose 2x. Okay, hopefully that's starting to make sense for you. Now let's add these up to get our equilibrium concentrations. 1 mole per liter minus 2x. 0 plus 1x is 1x. 0 plus 3x is 3x. Okay, so we have our equilibrium concentrations. Now there's got to be a way to find x. Let's go back and look at this. After equilibrium was reached, 0.399 moles of nitrogen was found in the flask. Okay, so 1x is 0.399 moles in a 1 liter flask. Okay, so we have x. X is, whoa, let's try that again. X is 0.399 molar. So now we can substitute it into there, and we can substitute into there. And that is 0.202. Let's keep things simple on our sig digs, and we'll just go with 3 sig digs for all of these guys. And 3 times, what were we? 0.399 is 1.197. We went with 3 sig digs, so we get 1.20 molar. So there's our final equilibrium concentrations of our 3 substances. So that's concentration of NH3, concentration of N2, and concentration of H2. Again, I apologize for being messy, but as long as you get the patterns and the process, that's what's key today. Okay, take a breath. Take a look at it. 1 left to do. I think this is a change from the one that's in your study guide. I think I changed that to 3 moles. That's why it's in red. All right, last one. In a certain experiment, we have 3 moles of SO2, 2 moles of O2, and 4 moles of SO3 placed in a 1 liter vessel. Now, this doesn't tell you the reaction, so I'm just going to give it to you. SO2 reacts with O2 and will reach equilibrium to make SO3. These are all gases. Whoops, gas. Okay. Balance it. 1 sulfur, 4 oxygen, 3. So I'm going to need to put a 2 in front of there, which means I need to put a 2 in front of there. 2 sulfur, 6 oxygen, 4, 6 oxygen. Okay, we're balanced. So we are going to need to make an ice table to organize all of our data. So concentrations. So you can see how we just set them up right under the balanced equation. Okay, what have we got? Initially, 3 moles, and it's all in a 1 liter flask, so 3 moles per liter. Oxygen is 2 moles per liter, and sulfur trioxide is 4. Okay, so this is one of those questions that's like this guy, where is it? Right here. You're starting with a mixture of reactants and products. So this is a little trickier. So which way does this thing move to reach equilibrium? The first two examples went forward. It was easy. They went to the zero. Whichever way the rule is you always move to zero. I should write that down. Always move to 0 moles per liter, but there are no zeros here. So how do we figure it out? After the system reached equilibrium, we had 3 moles per liter of SO3. So it's telling us that at equilibrium, we're at 3. So we started at 4 and we went to 3. Which way did this thing move? Forward or reverse to turn 4 into 3? It had to go in reverse to reach equilibrium. So if it went in reverse, that means we lost product. How much? 2. Let's change up our colors here. So we lost 2 amounts of SO3. If it's going in reverse, that means we gained 1 oxygen and we gained 2 SO2. So lost 2x, gained 1x, gained 2x. So at equilibrium, we started with 3 moles per liter and we gained 2x. We started with 2 moles per liter and we gained 1x. We started with 4 moles per liter and we lost 2x, and we have the answer. 3 moles per liter. So this is how we solve for x. So 4 moles per liter minus 2x equals 3 moles per liter. Rearrange it all and solve, and x is 0.50. Okay, now we have x. We can substitute it in to there and there. 2.00 moles per liter plus 1x is 2.50 moles per liter. And this one is 3 plus 2x is 4 moles per liter. There's our 3 equilibrium concentrations. So concentration of SO2, concentration of O2, concentration of SO3. Aren't ice tables easy? Yes, they are. Okay, so practice. Textbook. There are 3 good questions. I'll make sure that the solutions are posted for those because they are thinking questions. There is an equilibrium assignment to do. It's 2 pages in your guide, but we can only do numbers 1 to 7 today. Tomorrow will be, I think it's 8 to 11, the back side of it. But today, just numbers 1 to 7 to practice and try those textbook questions. And there's a little hint here for number 6. You must use initial concentrations and add these to the graph. 6 is a very tricky little thinking question. It's kind of like how I started off today with this graph. So they give you a graph like this, and you have to figure out these numbers using that big, beautiful brain of yours. So if you get really stuck on 6, you can take a look at the solutions for it. It is a good thinking question. And then numbers 1 to 7 are pretty straightforward in the study guide. Okay. Hopefully you're good to go on that. Ice tables, we use them every day in equilibrium. So you really need to get good practice. Please do these questions. The sooner you get this dialed in, the better the chapter is. It's kind of like in redox how you had to learn oxidation, reduction, Auger, Rayleigh, and apply those because you use them throughout the rest of the chapter. All right. Have a good day, everybody. And tomorrow we'll continue on with